All right. So I'm going to keep this sign up. I have a 31-day challenge sign up next to me. I'm not going to be working on it right now. I'm going to be doing some organic chemistry because that sounds really fun right now. And I like what's fun. So let's go ahead and zoom in. 150. Nope, too far. 125. That should do. 10th edition. Let's go to bookmarks. Chapter 1. Let's get straight into it. Let's close that up. Okay, now we can zoom in. Probably one more. 50. Let's do fit the width. There we go. Okay. All right, so this is OpenStax Organic Chemistry. They just uploaded it pretty recently, I think in the last month or two. So that's why I wasn't a part of this original list, because I hadn't considered it. But let's go ahead and do it now. I'm not going to do anything on the whiteboard. The live stream is just if anybody just happens to pop by and wants to leave a comment or wants to request tutoring or anything, like just go ahead and I guess leave me whatever information you need to leave me for me to contact you. But if anybody sees it. But anywho, until I start getting a following, I'm just going to go ahead and get into this. Chapter 1, structure and bonding. So picture that it shows at the very beginning, that is a folded protein structure using digital program. I forget what program I use for stuff like this. I've used a couple. But basically, each of these structures, if you look right here, I'm going to go ahead and draw a circle. Oops, hold on. This one. There we go. Draw a circle right here. Here, some purple ones. See these little coil structures? Those are helixes, alpha helices. Oops, this isn't though. That's a beta sheet. And then these big flat arrows, that's a beta sheet. And it's just an orientation of how the different molecules align with each other and how they bond, how each of the different atoms bond together. Pretty cool stuff. This is basically a summary of what a protein might look like when it's not vibrating and moving and all that stuff. Oh, yeah, figure 1.1. HMG-CoA reductase, shown here, so-called ribbon model, catalyzes a crucial step in a body synthesis of cholesterol. And so basically, yeah, what you can do is each of these colors, if I remember the terminology, is a domain, and each of the domains has a specific function within the protein. Sometimes the function is purely structural. You'll see some really cool bends and stuff that even have some specific names because there's certain patterns that they might follow. And then there's like the active site where the protein actually does the work on whatever it's working on. So, yeah, the way these things work is really cool. All right, chapter contents. I'm not going to read those because I don't care. Why this chapter? Don't care. Okay, maybe I'll read what they have to say. Every living organism is made of organic chemicals, the proteins that make up your hair, skin, and muscles, the DNA that controls your genetic heritage, the foods that nourish you, and the medicines that heal you are all organic chemicals. Anyone with a curiosity about life and living things, and anyone who wants to be a part of the remarkable advances taking place in medicine and the biological sciences must first understand organic chemistry. Here's a fun fact, though. None of those sciences has figured out how to make life on their own without the very limited... Actually, I don't even know if they figured that out. I know there's a Dr. James Tour, who's an organic chemist. I don't remember where he teaches at. I forget if he's Jewish or Christian. He's a monotheistic chemist. He's pretty good. He's really fun to listen to. But he claims that the biological life still hasn't been figured out. Yeah, we have the theory of evolution, which I do believe in evolution. Like, I've evolved so much in the last couple years just by shifting the way that I think about the world and the way I understand things, the way I understand my interaction with the world. And so it's helped me evolve into, I'd say, a better human, for sure. Yeah, I'm a lot more compassionate. Yeah, I'm a little bit more unwilling to change my mind on certain things, but that doesn't mean I don't respect another person's choice to make those decisions. So, um, but yeah, it's still really amazing stuff. I love the organic chemistry lab. It's like you get to actually play with the building blocks and build up new puzzles and stuff. It's pretty sweet. Okay, so anyone look at the following drawings, for instance, which show the chemical structures of some molecules whose names might be familiar to you. Although the drawings may appear unintelligible at this point, don't worry. They'll make perfectly good sense before long, and you'll soon be drawing similar structures for any substance you're interested in. I've always loved these line structures. So basically, um, instead of drawing, say, like this part right here, that's a benzene ring. So instead of drawing it like that, oops, let's make that a little bit smaller. One sec. To the eraser. There we go. Okay, C. If you were to draw it using a regular Lewis structure, this is what that part would look like. And then you'd have a hydrogen there, hydrogen there, hydrogen there. Basically what this is just shortcut. And then you have another ring here. That was a bad one. And then you have oxygen, carbon, and then OCH3. So basically that little section, that's what it would look like as part of the Lewis structure. I forgot to draw the carbons in these couple spots. But basically every vertex that doesn't have an explicit atom is assumed carbon. And then you count the number of bonds on that carbon. And if there are less than 4 bonds to the carbon, you add additional bonds. You assume additional bonds go to hydrogen. And so, like, if you look at this carbon here, there's a hydrogen there, and there, 2 there. See, they put that one there, because it has to go there. Yeah, that's why they draw the hydrogens in. You see it's on a dashed line. I actually don't like the way they do these dashed lines. I prefer if I do a dashed line. So dashed line means the hydrogen is, if you were to imagine this is a 3D structure, the hydrogen is pointed towards the back of the screen. And then this is called a wedge. And the wedge means it's coming out at your face. So, but I like to do, if I do a wedge, I do sideways dashes, and there's my hydrogen. So that's just a way to do it. But that's oxycodone, cholesterol, and benzyl penicillin. And as you can see, there's a lot of interesting things on there. We got nitrogens, hydroxides, methyls, hydrogens, CO2s, sulfurs. I think I said sulfur already. I forget. Anyhow, but you got a lot of cool stuff. Historically, the term organic chemistry dates to the mid-1700s when it was used to mean the chemistry of substances found in living organisms. Little was known about the chemistry at that time, and the behavior of the organic substances isolated from plants and animals seemed different from that of the inorganic substances found in minerals. Organic compounds were generally low-melting solids and were usually more difficult to isolate, purify, and work with than high-melting inorganic compounds. By the mid-1800s, however, it was clear that there was no fundamental difference between organic and inorganic compounds. The only distinguishing characteristic of organic compounds is that all contain the element carbon. Organic chemistry, that's a word, then is the study of carbon compounds. But why is carbon special? Well, that's not necessarily true, because you can have compounds of carbon that are not organic, like diamond. But why is carbon special? Why, of the more than 197 million presently known chemical compounds, do almost all of them contain carbon? The answers to these questions come from carbon's electronic structure and its consequent position in the periodic table. As a group 4A element, carbon can share 4 valence electrons and form 4 strong covalent bonds. Furthermore, carbon atoms can bond to one another, forming long chains and rings. Carbon alone, of all elements, is able to form an immense diversity of compounds, from the simple methane with one carbon atom to the staggeringly complex DNA, which can have more than 100 million carbons. Oh, sorry, that's a plane. I was hoping that was thunder. By the way, just for clarification, anything I say in all of this that's not directly read from this book is an opinion of mine based on my own observations and my own experiences throughout my life. So mainstream organic chemistry might disagree with some of the things I have to say, like my questioning evolution. I do believe that we can evolve. I do believe it's more of a choice, but there's more to choice than just our own individual choices. There's other people's choices around me too. There's companies making choices. That's why pollution can cause issues and different things like that. So I don't claim to know the truth, but because I have done well historically in this class or in this course, and because I did well on the ACS organic exam twice, the first time getting in the 100th percentile, the second time I think it was like 93rd, because it had been a long time since I had studied it, but that's not really a good excuse. I should, as an organic chemist, I should know all the organic chemistry and not just some of it. But I would say that I have pretty good intuition when it comes to this stuff. So, but I could be wrong, and I'm perfectly willing to accept it with my own experiences. If there are experiences that I can demonstrate to show that what I'm saying is incorrect, then I'd be willing to do it. But I don't trust anybody else's research, especially when most of it requires money from billion and trillion dollar organizations that don't really have, I would say, my best future in mind. But I think my future's a little bit different, just because I've managed to change so much of it in the last couple of years, with thanks to all of the help that I've had, in addition to just kind of the more, I guess, spiritual awakening. I'm still going through what I would call that, connecting things. That's how I kind of describe spirit in the most general sense. It's the connection between all things. And so, but sorry, I didn't mean to get off topic there, but I just wanted to let people know I've put a lot of thought into this if anybody sees this. So, anywho, let's see. As a group 4A element, carbon can share 4 valence electrons and form 4 strong covalent bonds. Furthermore, carbon atoms can bond to one another, forming long chains and rings. Carbon alone, of all elements, is able to form an immense diversity of compounds, from the simple methane with one carbon atom to the staggeringly complex DNA, which can have more than 100 million carbons. Which is a lot. And then, looking at this chart here, the main elements in organic chemistry are hydrogen, that row, and then these two. So hydrogen, carbon, nitrogen, oxygen, fluorine, phosphorus, sulfur, chlorine, bromine, and iodine. There are some places for boron. Actually, there's actually probably a whole chapter. I didn't check the table of contents, but I remember there being quite a bit of stuff that can be done with boron. Lithium is going to have some stuff. Sodium will have some. Magnesium will have some. Aluminum will be in there somewhere. And you might see some of the heavier metals like platinum and cobalt for some of the not enzyme. What's the word I'm looking for? Catalysis. When that gets talked about. Okay, not all carbon compounds are derived from living organisms. However, Modern chemists have developed a remarkably sophisticated ability to design and synthesize new organic compounds in the laboratory, medicines, dyes, polymers, and a host of other substances. Organic chemistry touches the lives of everyone. Its study can be a fascinating undertaking. And one main organic compound that most people are accustomed to, that is acetic acid. That is vinegar. So that's an example of an organic compound that's used a lot. All right. 1.1, atomic structure, the nucleus. As you might remember from your general chemistry course, an atom consists of a dense positively charged nucleus surrounded by a relatively large distance by negatively charged electrons. The nucleus consists of subatomic particles called neutrons, which are electrically neutral, and protons, which are positively charged. Because an atom is neutral overall, the number of positive protons in the nucleus and the number of negative electrons surrounding the nucleus are the same. And then in this picture, you have the nucleus and the electron cloud that surrounds it. And you can see the relative size. The nucleus is very small compared to the whole electron cloud. Although extremely small, about 10 to the negative 14 or 10 to the negative 15 meters. Now remember, that's 0.000000 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, sorry. The one should go right there. That's the 10 to the negative 15 meters. So that's how many zeros you're looking at. That's unfathomable to the current human body's sensory perception, as far as we're aware, as far as I'm aware. Meter in diameter. The nucleus, nevertheless, contains essentially all the mass of the atom. Electrons have negligible mass and circulate around the nucleus at a distance of approximately 10 to the negative 10 meters. Thus, the diameter of a typical atom is about 2 times 10 to the negative 10 meters, or 200 picometers, where 1 picometer is 10 to the negative 12 meters. To give you an idea of how small this is, a thin pencil line is about 3 million carbon atoms wide. Although most chemists throughout the world use the international system of units and describe small distances in picometers, many organic chemists and biochemists in the United States still use the unit angstrom to express atomic distances, where 1 angstrom equals 100 picometers equals 10 to the negative 10 meters. As you probably did in your general chemistry course, however, we'll stay with SI units in this book. A specific atom is described by its atomic number Z, which gives the number of protons or electrons it contains. That's not a good way to do it because it could be an ion too. So should always just go with protons. It'll always be the number of protons. And its mass number A, which gives the total number of protons and neutrons in the nucleus. So it's the sum of basically all the mass units. All the atoms of a given element have the same atomic number, 1 for hydrogen, 6 for carbon, 15 for phosphorus, and so on. But they can have different mass numbers depending on how many neutrons they contain. Atoms with the same atomic number but different mass numbers are called isotopes. The element carbon, for instance, has 3 isotopes that occur naturally with mass numbers of 12, 13, and 14. Carbon-12 has a natural abundance of 98.89%. Carbon-13 has a natural abundance of 1.11%, and carbon-14 has only a negligible natural abundance. The weighted average of an element's natural occurring isotopes is called its atomic weight. It is given in unified atomic mass units, or daltons, where 1 unit, or 1 dalton, is defined as 1/12 the mass of 1 atom of carbon-12. Thus, the atomic weight is 1.008 units, 1.008 units for hydrogen, 12.011 units for carbon, and 30.974 units for phosphorus, and so on. Atomic weights of all elements are given in the periodic table in Appendix D. 1.2, atomic structure, orbitals. How are the electrons distributed in an atom? You might recall from your general chemistry course that according to the quantum mechanical model, the behavior of a specific electron in an atom can be described by a mathematical expression called a wave equation, the same type of expression used to describe the motion of waves in a fluid. The solution to a wave equation is called the wave function, or orbital, and is denoted by the lowercase Greek letter psi. When the square of the psi wave function, psi squared, is plotted in three-dimensional space, an orbital describes the volume of space around the nucleus that an electron is most likely to occupy. You might therefore think of an orbital as looking like a photograph of the electron taken at slow shutter speed. In such a photo, the orbital would appear as a blurry cloud, indicating the region of space where the electron has been. The electron cloud doesn't have a sharp boundary, but for practical purposes, we can set the limits by saying that an orbital represents the space where an electron spends 90 to 95% of its time. What do orbitals look like? There are four different kinds of orbitals, denoted S, P, D, and F, each with a different shape. Of the four, we'll be concerned primarily with S and P orbitals because these are the most common in organic and biological chemistry. An s orbital has a spherical shape with a nucleus at its center. A p orbital has a dumbbell shape with two parts, or lobes. Excuse me. And four of the five d orbitals have a cloverleaf shape with four lobes, as shown in figure 1.4. The fifth d orbital is shaped like an elongated dumbbell with a donut around its middle, which is arbitrary. That's something that I learned in inorganic chemistry. It was totally bullshit. There were supposed to be 6 equations, but they decided to make it 5 to be consistent with something. So that's what an s orbital looks like, p orbital and a d orbital. Okay. The orbitals in an atom are organized into different layers around the nucleus called electron shells. Excuse me. Which are centered around the nucleus and have successively larger size and energy. Successively. Different shells contain different numbers and kinds of orbitals, and each orbital within a shell can be occupied by 2 electrons. The first shell contains only a single s orbital, denoted 1s, and thus only holds 2 electrons. The second shell contains 1 2s orbital and 3 2p orbitals, and thus holds a total of 8 electrons. The third shell contains a 3s orbital, 3p orbitals, and 5d orbitals, for a total capacity of 18 electrons. These orbital groupings and their energy levels are shown in figure 1.5. And so it just shows how as the energy increases, the orbitals basically go up in value of energy. The 3 different p orbitals within a given shell are oriented in space along mutually perpendicular directions, denoted px, py, and pz, as shown in figure 1.6. The 2 lobes of each p orbital are separated by a region of 0 electron density called a node. Furthermore, the 2 orbital regions separated by the node have different algebraic signs, plus and minus, in the wave function, as represented by the different colors in figure 1.4 and figure 1.6. As we'll see in section 1.11, these algebraic signs for different orbital lobes have important consequences with respect to chemical bonding and chemical reactivity. And there it is right there. Px, py, and pz orbitals, they're all oriented differently on the same axes, but they're the same shape. They're just basically rotations of that shape. Okay, 1.3, atomic structure, electron configurations. The lowest energy arrangement, or ground state electron configuration of an atom, is a list of the orbitals occupied by its electrons. We can predict this arrangement by following 3 rules. The lowest energy orbitals fill up first, 1s, 2s, 2p, 3s, 3p, 4s, 3d, according to the following graphic, a statement called the Aufbau principle. Note that the 4s lines between the 3p and 3d orbitals in energy. And so basically you write it out in order 1, 2, 3, 4, 5, 6. However, you draw these diagonal lines pointed down through these. So 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 5f, 6d, 6f. Rule 2. Electrons act in some ways as if they were spinning around an axis, somewhat as the Earth spins. The spin can have 2 orientations, denoted up and down. Only 2 electrons can occupy an orbital, and they must have opposite spins, a statement called the Pauli exclusion principle. Rule 3. If two or more empty orbitals of equal energy are available, one electron occupies each with spins parallel until all orbitals are half full, a statement called Hund's rule. And so basically what that means is there's a specific order in which the electrons will start to fill. Some examples of how these rules apply are shown in Table 1.1. Hydrogen, for instance, has only one electron, which must occupy the lowest energy orbital. Thus, hydrogen has a 1s ground state configuration. Carbon has 6 electrons, and the ground state configuration is 1s2, 2s2, 2px1, 2py1, and so forth. Note that this superscript is used to represent the number of electrons in a particular orbital. And then you have a little table here. It just shows you what the configuration of each of these is. So we got some problems. What is the ground state electron configuration of each of the following elements? Oxygen, nitrogen, sulfur. Well, if I recall, oxygen is 8, nitrogen is 7, sulfur is 12 or 16, I think. So let's just look at a periodic table real quick. Table, oops. So yeah, oxygen is 8. So that's going to be 1s2, 2s2, 2p4, or sorry, 2px2, 2py1, 2pz1. Sorry, hold on. 1, 2, 3. Yeah, that's right. And then phosphorus or nitrogen will just be 2p x1 y1 z1 py1 pz1. And then phosphorus will be 1s2, 2s2, 2p6, 3s2, and then 3px1, 3py1, 3pz1. Okay. Oops. Yep. Oh, it was sulfur. Sorry. Sulfur's under oxygen, so just add one more. And then how many electrons? Fuck. I'll write it down here. 1s2, 2s2, 2px, 2py1, pz1. Nitrogen. It's going to be 1s2, 2s2, 2px1, py1, pz1. And then sulfur will be 1s2, 2s2, 2p6, 3s2, 3px2, py1, pz1. How many electrons does each of the following biological trace elements have in its outermost electron shell? Magnesium, it's going to be 2. Cobalt, will probably be 2 in the S. 1, 2, 3, 4, 5, 6, 7. So I'd say, what's that, 9? In selenium. Is going to be 6. Oops. Okay, 1.4, development of chemical bonding theory. By the mid-1800s, the new science of chemistry was developing rapidly, especially in Europe, and chemists had begun to probe the forces holding compounds together. In 1858, the German chemist August Kekula and the Scottish chemist Archibald Cooper independently proposed that in all organic compounds, carbon is tetravalent. It always forms 4 bonds when it joins other elements to form stable compounds. Furthermore, said Kekula, carbon atoms can bond to one another to form extended chains of linked atoms. In 1865, Kekula provided another major advance when he suggested that carbon chains can double back on themselves to form rings of atoms. See, that's crazy. 1800s, they were talking about this. And I don't know anyone in my personal life who is able to get that, besides myself, obviously, and the people that I studied with. Although Kekula and Cooper were correct in describing the tetravalent nature of carbon, chemistry was still viewed in a two-dimensional way until 1874. And that year, the Dutch chemist Jacobus van 't Hoff, the French chemist, and French chemist Joseph Lebel added a third dimension to our ideas about organic compounds when they proposed that the 4 bonds of carbon are not oriented randomly but have specific spatial directions. Van 't Hoff went even further and suggested that the 4 atoms to which carbon is bonded sit at the corners of a regular tetrahedron, with carbon in the center. A representation of a tetrahedral carbon atom is shown in Figure 1.7. Note that conventions used to show three-dimensionality. Solid lines present bonds in the plane of the page. The heavy wedged lines represents a bond coming out of the page toward the viewer, and the dashed line represents a bond receding back behind the page away from the viewer. We get used to them. These representations will be used throughout the text. And so that's basically they're saying that the tetrahedron, this little pyramid guy, looks exactly like what a methane molecule or just a carbon with 4 atoms bonded to it would look like. Why, though, do atoms bond together, and how can chemical bonds be described electronically? The why question is relatively easy to answer. Atoms bond together because the compound that results is more stable and lower in energy than the separate atoms. Energy, usually as heat, is always released and flows out of the chemical system when a bond forms. Conversely, energy is added to the chemical system when a bond breaks. Making bonds always releases energy, and breaking bonds always absorbs energy. The how question is more difficult. To answer it, we need to know more about the electronic properties of atoms. We know through observations that 8 electrons, an electron octet, in an atom's outermost shell or valence shell impart special stability to the noble gas elements in group 8A of the periodic table, where neon is 2 plus 8, argon is 2 plus 8 plus 8, krypton is 2 plus 8 plus 18 plus 8. We also know that the chemistry of the main group elements on the left sides of the periodic table is governed by their tendency to take on the electron configuration of the nearest noble gas. The alkali metals, such as sodium in group 1A, for example, achieve a noble gas configuration by losing the single s electron from their valence shell to form a cation, while the halogens, such as chlorine in group 7A, achieve a noble gas configuration by gaining a p electron to fill their valence shell and form an anion. The resultant ions are held together in compounds like sodium chloride by the electrical attraction of unlike charges that we call an ionic bond. But how do elements closer to the middle of the periodic table form bonds? Look at methane, CH4, the main constituent of natural gas, for example. The bonding in methane is not ionic because it would take too much energy for carbon either to gain or lose 4 electrons to achieve a noble gas configuration. Instead, carbon bonds to other atoms not by gaining or losing electrons, but by sharing them. Such a shared electron bond, first proposed in 1916 by the American chemist Gian Lewis, is called a covalent bond. The neutral collection of atoms held together by covalent bonds is called a molecule. Ionic compounds such as sodium chloride, however, are not called molecules. A simple way of indicating the covalent bonds in molecules is to use what are called Lewis structures or electron dot structures, in which the valence shell electrons of an atom are represented as dots. Thus, hydrogen has 1 dot representing its 1s electron, carbon has 4 dots, oxygen has 6 dots, and so on. A stable molecule results whenever a noble gas configuration of 8 dots is achieved for all main group atoms or 2 dots for hydrogen. Even simpler than Lewis structures is the use of Kekula structures or line bond structures, in which the 2 electron covalent bonds are indicated as lines drawn between atoms. So you have draw 2 dots, or you can do the line, and that represents the same thing. The number of covalent bonds in an atom forms depends on how many additional valence electrons it needs to reach a noble gas configuration. Hydrogen has one valence electron and needs only one more to reach the helium configuration, so it forms one bond. Carbon has four valence electrons and needs four more to reach the neon configuration, so it forms four bonds. Nitrogen has five valence electrons, needs three more, and forms three bonds. Oxygen has six valence electrons, needs two more, forms two bonds, and the halogens have seven valence electrons, needs one more, and form one bond. Valence electrons that are not used for bonding remain as dots in the structures and are called lone pair electrons or non-bonding electrons. The nitrogen atom in ammonia, NH3 for instance, shares six valence electrons and three covalent bonds and has its remaining two valence electrons as two dots in a non-bonding lone pair as a time-saving shorthand. Non-bonding electrons are often omitted when drawing line bond structures, but you still have to keep them in mind since they're often crucial in chemical reactions. All right, worked example 1.1, predicting the number of bonds formed by atoms and molecules. How many hydrogen atoms does phosphine have? Phosphine bond or phosphorus bond to in forming phosphine. So basically, let's go ahead and draw out the number of valence electrons. Phosphorus, gosh dang it. Let me just scratch that out. P, you have 1, 2, 3, 4, 5. So I've always done it. So that's basically like saying, there's my 2s, px, py, pz. Not the same orientation, doesn't have to be right now. But because it has three valence electrons, it's going to want to share those three valence electrons. So I would assume that we would get three hydrogens. Solution. Phosphorus is in group 5A of the periodic table and has five valence electrons. It thus needs to share three more electrons to make an octet, and therefore bonds to three hydrogen atoms, giving pH 3. Worked example 1.2. Draw both electron dot and line bond structures for chloromethane. Easy. First one, second one. Boop, 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 boop. You assume it's bonded to everything. Boop, boop, boop. HCl. H. Doesn't matter which one I put it on. And then, I don't need that extra set of dots. I'll just be H, 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 C, L. And that's how they'll share it. Oh, sorry. Don't forget valence electrons. Okay, got to count the valence electrons. Carbon, 4 plus 3 plus 7 equals 14. That's 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So I need to finish filling. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. 2, 4, 6, 8, 10, 12, 14. Forgot that part. It's been a while since I've done this, but there you go. That's chloromethane. Draw a molecule of chloroform. So I'm going to go ahead and hit the next problem. Problem 1.3. Draw a molecule of chloroform, CHCl3, using solid wedge and dashed lines to show tetrahedral geometry. Okay, so that's going to be chloromethane, chloroform. So that's basically trichloromethane. You want to call it that? That's going to be C. I always do 2 on the lines, 1 on a wedge, and 1 on a dash. Normally, I'd put the hydrogen on the back dash wedge. You can rotate the molecule to do that. That's something I'll teach you how to do. Convert the following representation of ethane into a conventional drawing that uses solid wedge and dash lines to indicate tetrahedral geometry around each carbon. Okay, so that's going to be boop, 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 boop. Boop, 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 boop. Boop, boop, boop. Boop, 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 boop. Boop, 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 boop. Just like that. Here it is. What are likely formulas for the following substances? Well, that'd be, it has 4 valence electrons, so we need 4 of these. Aluminum, That's going to be right under boron. That's going to have 3. So that's a 3. Carbon. So that carbon is actually bonded to the hydrogen and the chlorine. So this needs to be a 2. Silicon is typically 4, so you need 4 of those. CH3, NH. Well, that nitrogen is going to be bonded to the carbon. That's how that works. Hydrogen is just, yeah, don't worry about putting it in between because that just makes it weird. So that means it's bonded to one thing already. One thing there has normally 3, so 2. CH3, NH2. Right line bond structures for the following substances showing all non-bonding electrons. Okay. A, so CHCl3. We just did that. Yeah, we just did that, so I'm not going to do that one again. H2S, that's going to be S, H, H, do, 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 do. CH3 and H2, it's going to look like this. And then methyllithium, it's going to look like Li plus CH3 dot dot minus. That's an interesting one. There's a reason why we use it. Why can't an organic molecule have the formula C2H7? 4 times 2. That's 8. So it should have 8 bonds. Missing electrons. Because it would look like this. Sorry. That's not what I meant. I got that backwards. I meant to say it's too many hydrogens. There's no place to put it. No place for hydrogen. The 7th. Yeah, where you're supposed to put it. You would break the octet rule by putting it somewhere. So, boop, boop. All right, 1.5, describing chemical bonds, valence bond theory. How does electron sharing lead to bonding between atoms? 2 models have been developed to describe covalent bonding, valence bond theory and molecular orbital theory. Each model has its strengths and its weaknesses, and chemists tend to use them interchangeably depending on the circumstances. Valence bond theory is the more easily visualized of the two, so most of the descriptions we'll use in this book derive from that approach, which means this book is incomplete. According to the valence bond theory, a covalent bond forms when 2 atoms approach each other closely and singly occupied orbital on one atom overlaps a singly occupied orbital on the other atom. The electrons are now paired in the overlapping orbitals and are attracted to the nuclei of both atoms, thus bonding the atoms together. In H2 molecule, for instance, the HH bond results from the overlap of 2 singly occupied hydrogen 1s orbitals. So that's what it looks like. The overlapping orbitals in the H2 molecule have an elongated egg shape we might get by pressing 2 spheres together. If a plane were to pass through the middle of the bonds, the intersection of the plane and the overlapping orbitals would be a circle. In other words, the HH bond is cylindrically symmetrical, as shown in Figure 1.8. Such bonds, which are formed by the head-on overlap of 2 atomic orbitals along a line drawn between the nuclei, are called sigma bonds. During the bond forming reaction, 2H radical to H2, 436 kilojoules per mole of energy is released. Because the product H2 molecule has 436 kilojoules per mole less energy than the starting 2H radical atoms, the product is more stable than the reactant, and we say that the HH bond has a bond strength of 436 kilojoules per mole. In other words, we would have to put 436 kilojoules per mole of energy into the HH bond to break the H2 molecule apart into 2H atoms. No, we would have to put in 436 per mole of HH bonds, H2 molecules, to break two H2 molecules apart. Sorry, two H2 moles apart to form 2 moles of H by itself. For convenience, we'll generally give energies in both kilocalories and the SI unit kilojoules. 1 kilojoule equals 0.2390 kilocals. 1 kilocal equals 4.184 kilojoules. Yeah, it seems right. Okay. And then it shows the energy when you put them together. How close are the two nuclei in the H2 molecule? If they are too close, they will repel each other because both are positively charged. Yet if they're too far apart, they won't be able to share the bonding electrons. Thus, there is an optimum distance between nuclei that leads to maximum stability. Call the bond length. This distance is 74 picometers in the HH molecule. Every covalent bond has both a characteristic bond strength and a bond length. And then there we see the energy diagram where you have the hydrogen atoms that are way too close together. So you have to have some sort of force pushing them together. And then where they're the most stable, negative 74 picometers, is where it sits ideally, but it's going to kind of bounce back and forth in that hill. And then when they're too far apart, then the energy approaches zero, which makes sense because magic. All right, one sec. Is this still recording? Okay. All right. 1.6. sp3 hybrid orbitals in the structure of methane. And I'm going to go ahead and actually stop this now because I forget. This takes actually a lot of memory. So let's go ahead and stop this now, and I'll go ahead and continue on later on.